In this video, I introduce structured probabilistic models in machine learning. The goal of many machine learning methods is to predict the joint probability over a very large number of random variables. However, computing a joint probability of all random variables can be very inefficient and difficult. Instead, we often convert a joint probability into product of many conditional probabilities. For example, to predict the joint probability of a sequence from W1 to Wn, we first calculate the conditional probability of each data in the sequence, and then use the product of conditional probabilities to calculate the joint probability. That is the solution to the original problem. Given three random variables, W1, W2, and W3, W1 influences W2, and W2 influences W3, but W1 and W3 are independent. A structured probabilistic model shows their relationship in the figure here. Then we can calculate the probability of W1 and the conditional probability of W2 condition on W1 and conditional probability of W3 condition on W2. And then from product of the conditional probabilities to calculate the joint probability, that is the solution to the original problem. Structured probabilistic model includes a directed model and undirected model. Directed models use graphs with directed edges that represent a probability of each node in graph condition on its parent. For example, given random variables A, B, C, D, and E, their directed graph is showing here. The joint probability of A, B, C, D, and E is computed using product of 5 conditional probabilities. This is the root. We have a PA, and we got all the conditional probabilities. For example, this conditional probability of B condition is parent A, and so on. And then I use the product of 5 conditional probabilities to calculate the joint probability. That is the solution to the original problem. One typical example of directed models is a neural network. The units in one layer is updated condition on the units in its previous layer. Undirected models use graphs with undirected edges that represent factorizations into a set of functions. A click C in a graph G is a set of nodes connected to each other. For example, one click includes A, B, and C. A click potential phi is used to measure the consistency of a possible connection in a click C. For example, we have a potential phi 1, we have a potential phi 2, and a potential phi 3. Given 5 random variables A, B, C, D, and E, their undirected graph is showing here. The joint probability of A, B, C, D, and E is defined as a normalized product of 3 click potentials, phi 1, phi 2, and phi 3, where Z is a normalized factor to ensure positive potential. The exponential of energy function E is used as to define a potential function. Namely, use a potential of negative E to define a potential function phi. For more details, please check with these references. Thank you.